Looking at some linear algebra for the data science slash ML things. Okay. Bases and rank. In a vector space, we are particularly interested in sets of vectors A that poses the property that any vector that is included in the vector space can be obtained by a linear combination of vectors in A. So we have some gosh, work. So this is not good. Save it. I also do. Oh, okay. So this is working again. We have some vectors. They are a set of vectors which is called A. These vectors are from the vector space V, and using the vectors inside of this set, let's call them B1, B2, and so on till, let's say, Bk. This set of vectors we can use, we can generate a vector V that is included in the vector space V, this capital V, just by a linear combination of these basis vectors. So these the set is, I think, the basis vector, the basis set of vectors. So these vectors are special vectors, and in the following we will characterize them. So generating a set of set and bases, generating set and bases, generating set and span. Consider a vector space V where we can add and multiply vectors, and the set of vectors A is x1, x2, and these are the basis vectors. So x1, x2, and so on, and these vectors are part of the vector space. I think if every vector v small is included in V, can be expressed as a linear combination of x1 till xk. A is called a generating set of V. Okay, the set of all linear combinations of vectors in A is called a span. If A spans the vector space, we write V equal the span of the basis set of this vector space. It is equal to the span of the set which is called A. My initial guess was, I think, that this is called the basis, as it is the base for this vector space. Anyway, let's go. So we have V is equal to the span um, of the set of vectors, which is from x1 till xk. Generating sets are sets of vectors that this is an expression. Generating sets are sets of vectors that span vector subspaces. Every vector can be represented as a linear combination of the vectors in the generating set. Now we will be more specific and characterize the smallest generating set that spans a vector sub or a vector space. The bases. Consider a vector space V. A is a part, can be but or equal to the V. A generating set A of V is called minimal if there exists no smaller set that A that's part of A and not equal to A and is a part of V. So we can say that if we have A, this set, and we don't have a smaller set that can span the whole thing, um, this is called the bases. This is called bases of V. The whole purpose of this revision or study or whatever is just getting the intuition and really understanding this in a deep level that satisfies my desire. So let's go. We have the let's oh man. We have the vector space V, and this guy is um a vector space, and B is a part of the V, and B is not equal to 5, then the following statements are equivalent. B is a basis of V. B is a minimal generating set. B is a maximal linearly independent set of vectors in V. Adding any other vector to this set will make it linearly dependent. Every vector x that is inside of the vector space V is a linear combination of vectors from B, and every linear combination is unique. With x equal, let me think about this. We have the A set of vectors that is consistent of x1, x2, x3, x4, and so on. So these are independent vectors. Every vector is multiplied by a scalar. Lambda 1, lambda 2, lambda 3, lambda 4, and so on. So this is why the lambda and this symbol over here What is the real difference? I see no difference. Okay, this may be the more standard form of this equation. I don't really know. It's, when I say that the summation from 1 to k lambda I b of I is equal to summation from 1 to k lambda, let this ipsi, I think, and b of I think that this guy is equal to this guy. Honestly, I don't really know, but let's forget about it. The important thing is the essence, I think, so let's go on. We have both of those guys are included in the real number um, set of numbers, and mm, b of I is included in the basis set of the vector space V. So yeah, that it follows that lambda I is equal to ipsi I. Okay, so in the R cubed, the canonical canonical standard basis is you know x, y, and z. One here, and one here. X, Y, and Z. Then Blender. So this is weird, honestly. It's here we have the x-axis, this guy, y-axis, and the z. Let's grab anything like this guy, GZ. Look, this is the z-axis. Anyway, let's go back to the book. This is the basis set of vectors for the R cubed vector space. X, Y, and Z. We have 1, 0, 0. Let's take a deeper look at this. This represents the X, this represents Y, and this represents Z. So different bases in R cubed are this canonical, or we can just play a little bit with this and this. Here we have A is linearly independent, but not a generating set, and no bases of the fourth degree. For instance, the vector 1 0 0 0 0 cannot be obtained by a linear combination of elements in A. Fine. So it doesn't mean that if we have a linearly independent set of vectors, that these vectors are bases for a specific vector space, unless it covers all the vector space that we want, to span. Remark, if a vector space V supposes a basis B, the preceding examples show that there can be many bases of a vector space V. There's no unique basis, however all bases poses the same number of elements, the basis vectors. We only consider finite dimensional vector spaces V. In this case, the dimension of V is the number of basis vectors of V, and we write the IM dimension V. If U is part of V is a subspace of V. Yeah, I get it. So we can have this line, which is a 1D vector space included in the bigger two-dimensional vector space. So yeah, it makes sense. We can have a vector span combination of vectors like this. These are bases for the 2D vector space, as it covers all the vectors here, and now. So these guys, okay, form a three-dimensional vector space inside of the four dimensions vector space. So let's say that we have a vector space that consists of 4 dimensions, but we only can generate a 3D vector space. Fine, I get it. So let's move on. What page are we in? So I think this is enough. You know what? Let's go to this point to sex 2 and complete the rest in the upcoming video. Yup, let's go. I just can control this a little bit more. So, okay. If and only V is equal to U is equal to V, intuitively the dimension of a vector space can be thought of a number of independent directions in this vector space. Remark, the dimension of a vector space is not necessarily the number of elements in a vector. For instance, the vector space, the span of 0 and 1 is a one-dimensional. So as I said earlier, here in this example, every vector in this, where did it go? I deleted it, I think. Let's go back. So every vector here is a 4-dimensional vector, but the span is a 3D vector space. Although the basis vector boths two elements, remark a basis subspace U span of these vectors is a part of R in dimension can be found by executing the following steps. Write the spanning vectors as a column, the matrix A. Determine the row echelon form of A. The spanning vectors associated with the pivot columns are a basis of U. Here, if these four are independent, they will form a 4-dimensional vector space inside of the 5-dimensional vector space. As they are independent, each independent vector gives us a new dimension. So, we are interested in finding out which vectors x1 till x4 are a basis for U. For this, we need to check whether are linearly independent, therefore we need to solve this equation. Fine. So let me clarify this a little bit. If we have x1, x2, and this is the first vector, this is the second one, this is the third one. When I say that these guys are independent, this means the summation of two of those or some of those can't be equal to the one of the others. So the full summation, if we brought the other side here, is gonna be 0. So the property of multiplying by a scalar, this will be associated with here. We will add these guys. We will have this as the scalars that is multiplied by the vectors, forming linear equations, and we have to, using this matrix, making it much simpler, we can figure out if these guys are linearly independent or not. So yeah, so as you can see, here we have let's complete the reading. Since pivot columns indicate which set of vectors is linearly independent, we see from the row echelon form that x1, x2, and x4 are linearly independent because the system of equations x4 Hmm. X1, X2, and X4. Yo, so that's it. We have to figure out, in other words, that C1 equals 0, C2 equals 0, C3, and so on. If all of those guys are equal to 0, that means all these vectors are linearly independent. If one of these is equal to the summation of a linear combination of any of the others, this means that this guy is dependent on those guys and is not is considered a redundancy, so it's doesn't bring any new dimensions, so we delete it to be more specific, you know, So I think we reached a good point today. Um, I think I can do better tomorrow if I have the time and the mental stability that can drive me to, study again. So thanks for watching this video. It's been about a month and a half from the last video I published on this YouTube channel. I kind of sad about this, but it's the matter of life. I have some rough things going on here and there in my life, so at least I'm trying to keep up. And thank you. See you in the next video. Peace.